Hi, my name is Atanas and I'm the creator and currently the sole contributor to Scio. Scio is a new and modern graph engine that will power a constellation of distributed knowledge graphs. This series is called Building Scio, and in the next few episodes I'll show you my progress. We'll work on some cool experiments and we'll dig deeper into the fascinating world of graphs. My hope is that some of you might find this interesting and would like to join me in this great adventure. In this first episode, I'll quickly explain why graphs are awesome, the problems they solve, and their main advantages. Next, I'll demonstrate to you why, in my personal opinion, the current models for expressing and storing knowledge are flawed. Finally, we'll dive deep into Scio. How does Scio solve the challenges from a different angle? Ready? Here we go. Graphs are awesome. The fundamental building block of a graph is the triple: subject, predicate, and object. Where subject is a node, predicate is a property, adjective or a verb, and the object is either another node or a value, like a string, integer, or float. Here's a good example. Peter is 30 years old and he loves Maria. That's convenient as they both live in Paris. This simple model allows us to express any information. Graphs are the common denominator. Graph helps teams express data more freely. Let's say that we work in a large enterprise with different R&D teams. Each team handles lots of highly interconnected data. Teams tend to store data using the stack they are most familiar with, as a JSON object in Elastic, multiple tables with foreign keys in relational databases, or represented as multiple key value pairs. Quickly, we end up with multiple creative solutions that need supporting and training personnel. Graphs come to the rescue. From the most complex to the simplest of structures, graphs can express any information. The graph language is the common denominator. But graphs have also meaning. Let's take this example from a document in Elasticsearch. If you're part of the team that created and maintains this structure, the information contained in this object is clear to you. Maybe it's even described in some wiki or internal document. How about another team that would like to use it? This structure is full of ambiguity. Is Peter the parent of George, or George is the parent of Peter? Whose sister is Maria? Directed graphs eliminate this ambiguity. Let's see how. This document expressed as a graph looks like this. We clearly see the relations between Peter, George, and Maria. Graphs remove ambiguity and bring clarity. Okay, clearly graphs help us with unifying the structure of highly interconnected data. But still a problem persists. Even though two teams will use graphs to express data, given small differences in their inputs or their own understanding, the output will be quite different. Let's see this example. We have two teams. Team A receives the following input. Peter is the father of Maria, who is 10 years old. Team B, on the other hand, receives the following. Maria was born in 2013 and she is the daughter of Peter. Clearly we have a problem, as both teams receive the same information, just expressed differently. They should have outputted the same graph. What we need is a common guidebook on how knowledge should be expressed. This guidebook is called a schema. So what is a schema? Schema contains a list of properties and relations, defines use cases, exceptions, constraints, etc. Only schema-defined properties and relations can be used. Scio introduces numerous improvements over existing schema understanding. We'll discuss those improvements in later episodes. But here are a few teasers. Scio schema is a graph that defines itself. It defines and contains different types of nodes. There are no properties or relations, only nodes and values, and it's expandable. Getting back to a previous example, we define a simple schema that contains three properties: a name, a parent, and date of birth. Applying this schema forces both teams to express the knowledge the same way. Think of it this way. Schema makes all graphs speak the same language. So let's recap. I believe that graphs aim to facilitate teams to collaborate by expressing the data in the same way and using a common language. So, what are the components of a successful knowledge graph? To fully take advantage of graphs, you need the following. First, a simple yet highly scalable and performant graph engine that allows storing and manipulating complex graph data. Secondly, a rich and expandable schema ensuring knowledge is expressed in a unified and predictable manner. And there's a third element needed, but we'll discuss this one in the next episode of Building Scio. Why another graph engine? The question is, why build another graph engine? Don't we already have a lot of good software? Well, for me, the short answer is no. That might be the reason why still, after so many years and availability of mature products, graphs have not taken the world by storm. Hear me out. It's true that good solutions exist. Neo4j, Tiger Graph, Redis Graph, AWS Neptune, Nebula, MemGraph, just to name a few. When you visit their websites, each claim to be the fastest and the most scalable. But you see, I don't believe that this is that really important. The problem I personally have is that current solutions do not represent knowledge in a way that makes sense in the real world, or at least a way that makes sense to me. Let's see what I mean by this. Let's take a closer look at the label property graph model. It is used by many graph engine solutions. For this video though, I'll rely on Neo4j because it's the most mature, by far the most popular, and it has an awesome UI. So what is the label property graph model? We have nodes that contain two different data points, labels and properties. We use labels to group similar nodes. Think of labels as types. For example, the nodes that represent me could have labels human, father, author, etc. Properties are key value pairs that describe the node. For example, age 30, date of birth 1990, etc. Two nodes are connected via a relationship that has a unique type and properties similar to the nodes. Let's take this simple example. We have two nodes with common label person connected via a relationship of type love. The main advantage of the property graph model is that it's simple to understand. In theory, it just makes sense. That is until you start using it in real life. Here are some of the issues we will explore in the next minutes. In the node of the label person, how do we add multiple names, like aliases? How about language-dependent names? Example, in Russian, Peter is Pyotr. What is kg? How do we represent measurement dimensions in a scalable and a clear way? Is 1990 an integer, string, or datetime value? How do you express uncertitude? Why relationships are duplicated when no new information is added to the graph? The LPG model has limited expressiveness. Let's take this simple example to illustrate this. According to Wikipedia, the population of Amsterdam in 1990 was 800,000 people. To successfully encode the above, we need to create two nodes, one representing Amsterdam and the other the source, in this case Wikipedia. We create a relationship between the two. The question is, how do we add the properties to the Amsterdam node? At first, it seems easy enough. We just create the population and the date property. There are two problems with this approach. First, properties are key value pairs. This means that any new information, example the population in 2023, will simply override the previous data. The second problem is ambiguity grows as new data is added. Let's say that we learn that the area of Amsterdam is 200 square kilometers. In that case, we're not sure to which data point the property date refers to. What got measured in 1990, the population or the area? Another solution that I think is even recommended by Neo4j is to create artificial nodes to hold this information. We can create a node with label population that contains a pair of properties, population and date. Then we create a relationship connecting Amsterdam to this new node, also connected to the source of the information, the Wikipedia node. Another option is to take advantage of the fact that relationships support properties. We create a population node having a single property, population. We connect Amsterdam to this node via relationship that holds the property date. In my view, this solution is not good. The need to create artificial nodes overcomplicates the graph, making it harder to iterate, traverse, and understand and manipulate. This also heavily reminds me of the Freebase CVT model, where CVT refers to compound value types. From history, we know that this model is extremely inefficient. Now that we have a good grasp of the theory, let's dig into the code and examine more examples. So, let's have some fun with playing around with Neo4j. My current setup is really simple. I have a Docker image running on my laptop. The UI is running in the browser. And I've created some boilerplate code that will help us with the experiments. Every time we run the code, a delete function will be called to clean the graph, and we always have the same empty state. So let's run our first code where we're going to create a first node. Let me clean that quickly. Okay. So our query is create a new node, and the node will have a property name, and this property will have a value Peter. Cool. Let's run this code quickly and see the output. There we go. A node is created and it has a property name Peter. How about if now Peter had two names, Peter in English and maybe Piotr or George in any other language? How are we going to do that? Well, if we're directly writing it like so, we basically we're going to override it. Let's say that we have a match, and it's going to be any node because we only have one node, and we say the name. So set the name to be equal to name1 variable, and name1 variable this time is going to be I don't know, Piotr, for the Russian transliteration. What will happen if we run this now? Building, running, checking the results. We only have Piotr. So the second query has overwritten the previous one. So how do you solve this? If, for example, a person has multiple names in different languages. So one of the things and possibilities is to say, okay, this property is in English, while the other one will be set e-name in Russian. Like so. In this case, if you run the query and we verify the results, we have exactly what we wanted. Unfortunately, this means we have to create properties for each language. The other is to create these fake nodes and relations. And you can go to Stack Overflow. There are many questions concerning this problem. How to deal with language-dependent information and strings. Cool. Let's try to run something else. So I have prepared a very quick example here. Let's now create an array. So this will be our code. Simple enough. Let's go over it. We're creating a name, and this time the Peter, the property name will hold not a string, but an array, and the first element will be Peter. Let's run this quickly. Yes, I confirmed that there's an array, and the first element is Peter. Now, what will happen if we add to this array another element? We'll run again. This time we're going to merge the existing node, and we have only one in the database, in the graph, and we're going to set that the new value of the property name will be the old one plus whatever we pass in the function in this time, and we're going to say here maybe Piotr. And we're executing the query, saving. We run, and now we have two elements in the name, exactly what we expected. Now, what will happen if we copy and duplicate Peter once more? I personally would expect that it will not be, we're going to at the end only with the Peter and Piotr. Will that happen? Let's see. So our node now has two Peters and one Piotr. So the data got duplicated. It's a quirk, and we have to be aware of it. Now let's try to do something else, and this is the unpredictability on and not enforcement of data types. Let's run this simple example. Okay, let's go over the code. So creating two nodes, A and B. The first node has a name that is the array of strings, and the second node has name, again the same property, but this time only a string. And this is really very common to happen when multiple teams work on the same graphs. We're going to create those nodes, and then we're going to match the existing nodes, and we're going to append a new name. Like we want to append George to both Maria and Peter. What will be the end result of that? Okay. The query has run. So we see that Peter and George, we have a name property. It's an array with both names present. Unfortunately, on Maria, the George was concatenated to the string Maria. And this is how we create inconsistencies in the graph. Let's work a little bit on relationship very quickly, and then we're going to move on. So let's run this simple query. We're going to create two nodes, Maria and Peter, and we'll create also a relationship between Peter and Maria. Simple. Let's run it and see the results in the browser. Oh, I ran it twice. It's fine. There you go. So we have the node Peter points to the node Maria with the relationship loves, exactly as we expected. Now, what will happen if we execute the query for creating the relationship multiple times? Like so. So find the node of type with name Peter, match and find the node with name Maria, and then create the relationship, and we're repeating this create the relationship multiple times without adding any new information to the graph. I personally expect that at the end we're gonna have only one single relationship. Let's see how Neo4j handles this. The two nodes, and we have many relationships between them, duplicated. There's no additional information or anything concerning that. Cool. I have to say that Neo4j has a special command for this, and it's called merge. And the command merge is very handy and handles and helps us exactly in those situations when something already exists, so that we reuse it rather than to create a new one. To demonstrate this, let's run it. And if we run the graph in the browser, we see that we have only one loves relationship, which is what we expected. The problem with merge, it means that every time we create a relationship, we have to check if such a relationship already exists. And this creates, this complicates and makes the query slower. Yeah. That's it with Neo4j. Let's move on. Let's take a look at Scio data model. Scio's model is heavily inspired by how Wikidata structures its knowledge. It is strongly typed, meaning that properties define the values and not types. And properties are actually nodes. As I mentioned before, Scio has only nodes and values. The main building block of Scio is a claim. A claim consists of three parts. First is the main statement. This is the primary information holder block. Then we have qualifiers, a list of statements that add context to the main statement. And metadata, a list of statements that do not influence the main statement or the qualifiers. Meta is perfect for, well, metadata. Great use of meta is keeping track of the claim source. To get a better understanding of Scio's model, let's examine the previous example. According to Wikipedia, the population of Amsterdam in 1990 was 800,000 people. The sentence is a claim. The main statement is Amsterdam has a population of 800,000. The claim has one qualifier. When was the measurement done? In 1990. We create a meta statement denoting the source as the Wikipedia node. As you can see, the building blocks of the source sentence are perfectly mapped into the Scio data model. No need to create fake nodes or relationships. Let's play with some code and see Scio in action. So, let's see how Scio handles these challenging situations. Here on the screen you see my boilerplate code written in Go. Every time we run this function, a new store, Scio store will be created. So every time we have an empty graph. And in this first example, we're going to create a node and we're going to assign property of name Peter to it. So here we go. Node 1, type new node, and nodes in Scio have two elements: the ID of the node and the graph to which it belongs. We're going to learn more about the multi-graph system in later episodes of Building Scio. Then we're going to create a second node of type property, and properties in Scio have two elements: the ID of the node and its object type. Properties in Scio are strongly typed. It means that they define what are the object types they accept. Otherwise, they throw an error. And here we create the first claim. So our claim is node 1, property 1, name, and type string Peter. We store the claim, and then we try to return everything in our graph store. Let's run this query. We have a problem. Haven't stored it. And we run. So this is the result from the graph store. So we have a subject of the claim, which is node number 1, property, name, and the object of the main claim is Peter. We don't have any qualifiers. No, we have meta. Cool. Let's now try to add a second name. So Peter has a second name, which will be Piotr. Remember? Let's try to do this. So we're going to create a new claim, claim number 2, and this time we add the name Piotr. We store the claim number 2 and we retrieve the results from the graph store. Let's build and let's run. So this time around we have two claims stored. The first is node number 1, property name has Peter. There's no qualifiers, no meta. And the second claim is again node number 1, name Piotr. There's no qualifiers, no meta. Cool. Now, what do you think will happen if we repeat the same name twice? Like claim number 3, and we're gonna say Peter. How many claims we're gonna end up in the store? Well, Scio understands that this is the same claim. There's no new information that has been passed. So naturally, without making any changes to the code, nor making any searches, Scio will only return 2 claims. Let's see that. Claim number 1, Peter, and claim number 2, Piotr. No new information has been added. Great. Let's try another example. This is about Maria, and we're going to create a relationship between Maria and Peter. Let's try to do that. Here's the code, and we're going to go line by line to understand it. So we're creating a new store. Node 1 has an ID 1 and it represents Peter. Node 2 will represent Maria. There are 2 properties we're creating. The first one is name and the object type is a string. The second one is loves and the object type is another node because we're going to point from Peter to Maria, so it's a node object type. Claim 1 will be we create the node Peter and we assign the first property his name. Then claim 2 will be Maria, and we assign her name. And claim 3 is going to be a relationship between Peter, property 2 is loves, and node 2 is Maria. We store these 3 claims, and we retrieve everything in the graph store. Let's see how it looks like. So we should see 3 claims in total. I forgot. Wait, I forgot to save it. Okay, let's try again. Cool. We should see three claims in the graph store. So this is the first claim. Node 1 is Peter. Node 1 this time points to nodes 2 with property ID 2. This is loves. And the third claim is node ID 2, which has the name Maria. That's cool. So now if we take this claim that the relationship between node 1 and node 2, and we multiply it as a claim number 4, how many claims we're gonna have in the graph store? Well, again, Scio will understand that there's no new information provided. So when we run this query, we're gonna end up again with three claims. So this is Peter, loves, and again Maria. So no matter how many times we duplicate it, we're only gonna see it the unique number of times we have. Cool. Let's try now a little bit more complicated query where we're gonna add some qualifiers and some meta. So let's go over this code together for us to understand what is happening. So we have node 1, Peter, node 2, Maria, like before. We have now three properties. Property number 1 is name with expected type string as an object. Property 2 is a type node as an object, which represents loves. And now I have a new property, property 3. This time it expects a type datetime. And this will represent the property at. So we're going to have some date information. So claim number 1 will be we're creating the node Peter and we assign the name. Claim number 2, we assign and create the node Maria. Now this time we'll create a new datetime object like so. And when we create datetime objects in Scio, we also have to specify what is the precision. For example, if we know that they love each other for 2013, right? We don't know which month, we don't know which date, but it's in 2013. So this is where the precision comes in. So we create the third claim saying that node 1, Peter, loves Maria. And now we add a qualifier to this claim. Remember, the qualifiers add context to this information. And in this case, we add property number 3, which was at, and expecting a datetime value type, which we created previously. So we say that Peter and Maria love each other from at some point in time. Now, what will happen if we repeat the same information a second time? Right? Again, like before, because there's no new data, although we have 4 claims that we're gonna send to the engine, in fact, only 3 will be stored. Let's see that in action. So it's a little bit more complicated this time, but let's have a look. So this is Peter node, and Peter loves, and it points to node number 2, Maria. This time around we have a qualifier, and we have only one qualifier, which says it's property number 3. Remember, this is at, and then we have the object defining the datetime value. Here we have also the precision information. So we know that when we parse and we display this, we need to return only the year rather than the whole datetime object. There are no meta information attached to this claim. And at the end, we have node number 3, which is Maria. So what will happen now if between claim number 3 and claim number 4, they're absolutely the same, right? They're pointing Maria and Peter, they love each other, and the qualifiers were the same. So Scio understood that there's no new data, so it merged them into a single claim. But what will happen if now the qualifiers are different? Let's try this. So in this case, we will do, let me check how to do it. I'll directly paste a new code and we're gonna go step by step to understand what's happening. Okay, node 1, node 2, this is clear. We have again the 3 properties. We create the two claims where we create Peter, initialize Peter and Maria. And now we say with claim number 3, we say that at some point of time, which is now, Peter loves Maria. Then we're going to wait 5 seconds and we're going to create a claim number 4 and we're going to repeat this information. But this time around, don't forget that the time is 5 seconds later. So the 2 qualifiers are different. We store again the 4 queries, the 4 claims, and we try to retrieve everything. Let's try to do this. I don't know why it took a little bit like time. Let me just reload very quickly. It should be quite fast. Oh, it's the 5. Oh, of course, it's waiting for 5 seconds. I forgot. Cool. So now we have four claims in our graph store. So this is Peter. Then we have loves. This is the first love that we see. And we see the qualifier. And it's 44 seconds of today's date. But then we have a second claim, love again, and this is 49 seconds, right? So 5 seconds later. So Scio understood that the qualifiers are different, so it kept the claims separated. Nice. Another cool example is how meta works in Scio. Let's look at this code and go line by line. We create 2 nodes. Node 1 is Peter. Node 2 is Wikipedia. We create 2 properties. One is for name, and its object type is a string. And the property 2 is the source with type node as object type. Now we create 2 claims. Claim 1 assigns to node 1 the property name Peter, and claim 2 to node 2 the name Wikipedia. Now we create a third claim, and this time we repeat the same information as before. So we assign the name Peter to node number 1, but we add meta information that we know that this is coming from Wikipedia. We store the 3 claims. How many claims do you think we have in the system now? Let's test this. Here's the result. This is the node Peter, and it has meta information described as meta of ID number 1. And a second claim, which is the node and the name Wikipedia. So Scio understood that the first claim was lacking meta information, and it was okay when it received the third claim, where we learned that in fact Peter, and we have the source coming from Wikipedia, it was safe for those two claims to be merged, and it merged them automatically. No need to do anything in the code. Yeah. Let's continue with the rest of the presentation. So, what's coming in the next episodes of Building Scio? Well, my plan is that on the next episode, we'll try to import the entire Wikidata dataset, including qualifiers. That's 100 millions of nodes and billions of statements. And we'll try to run some cool queries on the data. On a later stage, we'll create some embeddings on all the nodes and activate Scio vector search capabilities. We're getting started with graph neural networks. We'll see how to create and maintain a schema, how to merge graphs and reconcile nodes, and maybe build some cool APIs like node disambiguation, context extraction, property predictions. I have many more ideas, but we'll see how it goes. So thank you very much for spending your time with me, and I hope to see you on the next episode of Building Scio. Ciao everyone!